Our next speaker is Jay Zhao from Georgia Tech, speaking on robust task and motion planning for agile locomotion in the now.
All right. Good morning, everyone. So thanks for the intro, Art, and I also want to thank the dynamic walking community inviting me for this talk. So today I'm going to talk about some of our recent work on high-level symbolic planning for agile locomotion in complex environments and how to reason about the safety and the robustness. I do want to say this work provides a different way to solve context sequence planning problem from the high-level perspective. So to start, I would like to motivate a little bit of our work using this one of the oldest extreme sport in Netherlands, which is called Fierljeppen. I hope I pronounced it correctly. So in this sport, each athlete is given a long pole, and they need to use this long pole to swing its body over the water and land on the sandbed on the other side. If we treat this whole motion as a motion planning problem and decompose it into multiple different phases, we can see this motion is composed of a sprint to the pole, jumping, grasping, and climbing to the top of this pole, while at the same time maintaining the body moving forward properly. And here we can see how to plan the motions during each phase and when to switch to the next phase are all critical for a successful run. And this is definitely a highly dynamic locomotion problem involving interactive dynamics and the sequential task composition. This scenario motivates us to question whether robots can achieve such level of agile behaviors and how to make contact decisions properly. And deviating from bipedal locomotion, in this study, we have a large focus on generalizing the locomotion behaviors to multi-contact scenario using all limb contact. And this locomotion scenario in constrained environments do have real-world merits and applications, such as the Thailand cave rescue and the ongoing DARPA subterranean challenge. From a high-level perspective, a fundamental question we are interested in is what type of decision-making and planning algorithm do robots need to achieve very agile, robust, and reactive behaviors through contact. And as we all know, I think contact problems have been widely explored this year, and multiple lines of research have emerged, such as like trajectory optimization, solving contact sequence, and people use simplified locomotion models to plan for the locations, multi-contact planning from humanoid community, and the more recent work like learning contact model, soft contact model, involving either numerical or physical softness, and a lot of bio-inspired works from animals and humans. However, I do want to say, I think among all of these works, we still means a general planning framework that can address a variety of environmental events and make the robots respond to these events properly. We have been working on this direction for the past few years and taking a completely different route. As presented in the previous dynamic walking, we have a large focus on reactive task planner synthesis by formulating this whole body locomotion planning problem as a two-player game. So the goal here is synthesize a winning strategy such that the robot can always win the game, and which basically means the robot can successfully maneuver this constraint environment. To achieve this goal, we employ a temporal logic-based motion planning approach to synthesize correct by construction winning strategy, which is represented by the automata. And here I show a fragment of this automata on the right. As we can see here, this automata incorporates a set of discrete states, including the environmental event states, robot keyframe states, contact configuration, and the locomotion mode. And I do want to comment out our two-player game is executed in a turn-based pattern. So the robot task planner responds to the environmental events within only one walking step. So that's why we call our method as planning in the now. As to the task specification, we get a lot of inspirations from real human locomotions, especially those seen in the parkour and the gymnastics. So we extract the essential locomotion dynamics, make the model abstraction. And in our study, we take into account a variety of simplified locomotion models, such as inverted pendulum model, pendulum multi-contact hopping, or even rimless model. And when the robot sense environmental states, it's going to make a decision on the sequential composition of this template model and generates the motion decision graph through the two-player game. And here are some results on integrating the high-level task planner with the underlying phase-based motion planning. And here we can see this robot can dynamically maneuver in this constraint environments using a variety of contact decisions. And even when some emergency events happens, the robot can, like, for example, the train get crashed, the robot can grasp the ceiling wall, or maybe a human appears in the scene, the robot is going to come to a stop and wait until the human disappears again. And we also generalize this locomotion behaviors to more complex situation. For example, if both terrain and the ceiling wall get crashed, the robot is going to initiate a leaping motion, or if the terrain gets a narrow passage, it's going to use a sliding motion through this complex terrain. So here, the locomotion phase-based trajectories in the robot center of mass space are sequentially composed through these symbolic decisions. And as I mentioned, the correctness of this sequential composition is guaranteed through this reactive task planner. But the problem is it's only guaranteed at the discrete level, at the symbolic level. So when we have low-level model uncertainties like terrain disturbance or external perturbations, this formal correctness guarantee is going to be broken easily, and it can cause failure at the low-level execution. So now the problem becomes how we can design or reason about the robustness at the discrete level and design corresponding robust planning strategy. So to address this, we propose a robust margin design using analytical solutions of our locomotion manifold. And as we all know, this locomotion manifold have this valley type trajectory profiles. And we derive analytical tangent cotangent manifold solutions thanks to the nice property of our locomotion models. And this manifold is used to design a non-Euclidean state space discretization. And this is a more advanced approach than just a traditional naive grid word discretization, and make our abstraction more consistent with the underlying locomotion dynamics. So based on this discretization, we propose a set of robust margins around this nominal keyframe state. And given this robust margin design, we have a systematic procedure to compute feasible robust keyframe transitions through the reachability analysis. And here are the steps. So first, we assume there is a nominal keyframe transition pair solved by the high-level symbolic planner for 2 consecutive walking steps, and the green cell represents this the nominal keyframe state. And then we are going to expand this nominal cell by using an epsilon radius and take the neighborhood cells into account as alternative keyframe transition pairs. And then through the reachability analysis, we can solve all the feasible robust keyframe transitions in this scenario. And here we can see when we have local state perturbations, these robust keyframe transitions allow a successful run by selecting alternative key transition possibilities. And so this is the pretty robust approach we propose to solve handle uncertainties at the low level. But there's one more problem. So sometimes the disturbance could be very large, and it can perturb the states out of this robust margin. And in this case, this keyframe transition approach will not work. So in our planner, we have another replanning mechanism to search for different locomotion modes and design corresponding keyframe states. So for example, in this scenario, the robot is going to initiate a hopping motion, but it's going to land for the next step, but it just realized that the next step also become crashed, and then it send a new command to the high-level task planner and ask for a new command. So basically grasp the ceiling wall and to achieve the successful run in this case. So at the last, I just want to maybe briefly mention an ongoing direction in our lab about summation and the task planning of heterogeneous robot teaming and navigation. So in particular, we are highly interested in collaborative behaviors involving locomotion, manipulation, and like aerial robots, and how to unify terrestrial and aerial coordination. And I want to say this problem is fundamentally more challenging than just the 2D mobile robot navigation due to the complexity of the locomotion dynamics. For example, when the robot makes a turn, we need to take into account the constraint from the underlying locomotion dynamics and incorporate them into the high-level task specification design. And here we propose a hierarchical framework for navigation in partially observable environment and reasoning about the safety from different perspectives. So as a takeaway message, for multi-context Agile, like the locomotion problem, there are great opportunities to export and leverage symbolic approach and like a temporal logic and AI planning method. And I think they can help us to explore the discrete structure of our planning and optimization problems. As to robustness, I do want to say it's very helpful for us to reason about uncertainties not only from the discrete, not only from the continuous level, but also the discrete decision level, and how to design robust discrete transitions and the robust margins. And if you're interested in hybrid locomotion planning, we do want to emphasize the importance of unifying a variety of locomotion models and make the robots react to diverse environmental events. So with that, I'm going to stop. Thank you.
Okay, thank you. Do we have any questions? We have Chris Atkinson.
So there's a paradigm shift going on in motion planning, robot motion planning, away from methods that just find feasible trajectories to methods that optimize something. And this is also a huge issue in understanding biological motion. When is it, can we sort of, as in the last talk, predict motion based on optimization versus, you know, some transient motion that we cooked up on the fly and it's hard to describe with optimization. It seems to me this approach is all about finding feasible motions, which, you know, is in some sense old-fashioned AI, and there's no element of optimization in it.
Right. So yeah, thanks, Chris. Yes, I think that's true and not. And so in this framework, yes. So when we design the locomotion behaviors, so we mainly use the simplified models, and in this work there's no optimization involved. But in another work, I mean, we do like kind of solve optimization problems and take into account a variety of like physical constraints and cost functions to reason about what is the optimal solutions. And I mean, I didn't present in this talk, but let me see, maybe I have something I can comment a little bit more. Yeah, so I mean, this is some slides I didn't mention, but literally we can solve like a kind of whole body optimization, incorporating multiple different constraints like contact constraints, centroidal dynamics, whole body dynamics. But our whole idea is basically solve this problem in a kind of distributed way. And the block on the upper right, you can see this is the centroidal dynamics, and actually the AI planning approach I just presented can be incorporated here. And so for example, we have a set of simplified models, and at the same time taking into account all other different kind of dynamics constraints, and get kind of the optimal solution. But yes, in our current planning framework, we haven't incorporated this optimization problem yet. So it's definitely, I think computationally it's going to be quite heavy.
So that another paradigm issue though is, do you do this symbolic reasoning first and then search in a graph of options and sort of locally optimize each path through the graph? Or do you just use soft constraints and explore infeasible motions and essentially use gradient descent to get you to something that's feasible and optimal? So one way to phrase it is, should you do hard constraints or soft constraints?
Okay, I mean, I'm trying to understand the context a little bit more, like the soft constraint, hard constraint you are talking about in terms of the optimization framework.
Yes, one way to do
different.
Soft constraints is, for example, every possible contact point is contacting every possible part of the environment all the time. And you gradually figure out what it's actually going to contact by having weights that go up and down. One version of this is contacted variant optimization by Igor Mordach.
Yeah, I think I think the contact implicit treasure of the kind of community have explored a lot on this, like how to relax the constraints, like numerically, to make the algorithm more computationally efficient. But I do want to comment that in this work we didn't solve problem from this way, and so what we do is basically we discretize the environment, and for example in our situation we take into account like a discrete set of stair height and the emergency events, and there are like a discrete robot action states and the locomotion mode. So I want to say it's completely in the discrete reasoning domain, and not solving through the optimization method. Does that kind of answer your question? All right, thanks.
Okay, why don't we move on? I think we have a question from Jonathan Hurst.
Yeah, maybe this is an easy one, but what is your action space, or what are you commanding? Are you commanding positions? Are you commanding torques? Are you commanding, PD gains or compliances or impedance control?
Yeah, so this is a completely high-level task and motion planning, and we haven't touched anything on the low-level control. I mean, which is definitely very important. But we do have like models in our like a task planning. So we did basically use the simplified models, and there are control actions, which are basically your foot locations and your torso torque, but it's kind of the control action of your reduced order model.
Do you know then that a feasible robot could follow any of these trajectories, or how would it interact with an environment when it makes a contact when perception is noisy, late, and wrong? Yeah,
so again, I want to highlight I think there are a lot of like low-level uncertainties or disturbance or even perception inaccuracy, but our approach is basically abstract all of these kind of uncertainties or disturbance in the robot center-of-mass state. And if we can build up a mapping between these like detailed perturbations and uncertainties with the like center-of-mass state deviation, and then we can apply our high-level planning approach to address this uncertainty. So I do want to say the robustness is primarily reasoned in this high-level reduced order state space. Yep.
Understood.
Okay, I'm afraid we're going to have to end the discussion here.